Welcome back. In the previous video, we looked at an introduction to probability, and we talked about the rules of probability, the different types of probability. We looked at the addition rule and the multiplication rule. So let's proceed on the whole concept of the multiplication rule. So in the last video, this was what we derived as the multiplication rule. And if A and B are independent events, then this is the probability of A occurring and then B occurring in successive trials. So that's the interpretation right there. It's summertime or any other season in the year when you are watching this video, but irrespective of the season, I'm sure we all love to go to it for a picnic. And let's say for this picnic, I want to carry some fruits for my picnic. So I want to have a bag of fruits. And so I have in my bag, I have 3 raspberries, I have 2 banana, and then I have 4 grapes in my bag of fruits. Let me add 1 more raspberry. So I have 30. Now, let's do some computation. Let's solve some probability problems. So what's the probability that I drew a grape given that probability that I drew a grape and then drew a banana from my bag? And let's consider this with replacement. So meaning that, with replacement. So I drew a grape, put it back in the bag, and then drew a banana with replacements. So basically, this leads us to the multiplication rule. So we can use the multiplication rule formula. So this will be equals to the probability of a grape multiplied by the probability of a banana given that I drew a grape. So you express it in terms of the multiplication rule, and then you decide if G and B are independent, then this will be the rule that we're going to use. So how do we go about solving this? What's the probability of a grape, of drawing a grape? So that will be clearly 4 over 9, right? That's 4 over 9. What's the probability of drawing a banana given that I had drawn a grape from the bag? So that's clearly, and you see, I drew, so that's clearly 2 over 9. Okay. So the probability of a banana given that I had drawn a grape are independent. That is, drawing a banana is uninfluenced by the fact that I had drawn a grape before. So in that case, this is simply the probability of a G, multiply that by the probability of a B, and that gives us 8 over 81. Just leave it at that. Now, what about without replacement? So this is independent. So without replacements, what's the probability of G and B? Now this would be different. So the probability, this will be the probability, we're still using this expression, the probability of G times the probability of B given G. Now the probability of drawing a grape is still 4/9. Now what's the probability of drawing a banana given that we had drawn a grape without replacement? So we didn't put the grape back into the bag. So the sample size reduces by 1. So the banana here is still 2, the numerator, but the denominator is now going to be 8. And so this will be 8/72, which is 1/9. Okay. Let's look at another example. And you can see this is the multiplication rule in action. Now, without replacement, what's the probability of drawing a raspberry and then drawing another raspberry? That simply also equals the probability of a raspberry times the probability of drawing a raspberry and then a raspberry. Okay, how many raspberries do we have? We have 3. So the probability of a raspberry is going to be 3/9. Now, without replacement, probability of drawing a raspberry, given that we had drawn a raspberry, so we kept one raspberry outside of the bag. So that would now be, how many raspberries are left in the bag? We have 2 raspberries left. So that would be 2 out of, what's the sample size now? It's going to be 8. So that will be 2 times 3. So 2 year 1, 2 year 4. So that's basically 3/36. That's 1/12. Okay. Keep following? Awesome. Now, one more example without replacements. What's the probability of drawing a banana and then a banana and another banana? What's the probability? Is this an impossible event or not? So what's the probability of drawing a banana and then a banana and then a banana? First, how many bananas do we have in the bag? We have just 2 bananas. So clearly this would be an impossible event. It's impossible for us to draw a banana and then a banana and then a banana. But let's look at this in terms of the whole multiplication rule. So this would be the probability of drawing the banana times the probability of drawing a banana, given that we have drawn a banana, times the probability of drawing a banana, given that we have drawn 2 bananas. Okay. Now without replacements. So how do we solve for this? The probability of drawing a banana, we know we have 2 bananas. So that is 2/9. Now the probability of drawing a banana, given that we have drawn a banana and we did not replace it, means that we have in a basket, we are left with 1 banana, and the sample size is now 8. Now, what's the probability of drawing a banana, given that we have drawn 2 bananas already from the bag? So we're left with 0 banana. So that will be 0/7. And when we multiply all of that, that gives us 0. So this is impossible. It's an impossible probability. Awesome. Okay. So you guys are now masters of probability. You understand the conditional rules and all that good stuff. Very soon we'll talk about the Bayes theorem, one of my favorite theorem of probability, because it's a special application of conditional probability, which we have just taken a look at. But let's look at one other concept, which is very important, especially in the problems you're going to see in your homework assignments. And that is the concept of at least one. So what's the probability of complementary events? Complementary events with at least one. Okay. Now, sometimes it is easy to deal with the complements of a set than the set itself. So I'm asking for the probability of A. Sometimes it's easy to find the probability of A complement and then find the probability of A after knowing the probability of its complements. Now, what does at least one mean? So when we say at least one, what does it mean? It means one or more. One or more. So the complement will be what? 0. That is none. So the complement, so one or more. So the probability of getting 1, the probability of getting 2, the probability of getting 3, 4, 5, 6. When you add all of that, that's very complex. Whereas finding the complement is much easier because we're just finding the probability of 0. And when we know that, we subtract it from 1, which is the complementary rule, and we get the probability of 1 or more. You can see? So what we're saying here is that the complement okay, I love, why do I write it? So the complement is what? Is 0 or none. So what we are saying here is that the probability of at least one, the probability of at least one is equals to 1 minus the probability of none, of 0. So 0 or none. So that's what we're saying. So instead of me trying to find the probability of at least one, which is the probability of 1, the probability of 2, the probability of 3, and so on, I'm simply going to find the probability of none and subtract it from 1 to get the probability of at least 1. Now let's look at an example to make it much clearer. So let's say as an example here, we flip coin 3 times. And the question here is, what is the probability of getting at least one head? What is the probability of getting at least one head? Of course, it's easy to do because the probability of getting one or more heads. This is a very simple example. Why is it very easy to do? We know that the sample size will be 2 to the power of 3, which is 8. Now, at least one head is one head or more. There's only one event in which there are no heads, and that's when you have tail, 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 tail. So it means that the probability of at least one head is 7/8. Okay, that's easy to do. So we know the sample size, which we've seen earlier. So, and there's only one single event, which is tail, 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 and the rest is 1 or more. So that's 7/8. So that's 7/8. However, let's use this concept that we've just learned to solve the problem. So the probability of at least one head also can be seen as 1 minus the probability of no heads, right? The probability of no heads. Now, what is that? That's simply saying 1 minus the probability of all tails. So no heads means all tails. Now, what's the probability of all tails? So this is 1 minus the probability of having a tail, and then a tail, and then a tail. We have 3 tails. So the probability of drawing a tail, and then another tail, and then another tail. So that's how we interpret this. So in successive trials, a tail, and then a tail, and then a tail, and that's one procedure. Okay. So this is where the multiplication rules come handy. So this is 1 minus the probability of a tail times the probability of a tail given a tail times the probability of a tail given 2 tails have occurred. Okay, so this is simply equals to 1 minus the probability of a tail is what? 1 over 2. The probability of a tail given that a tail has occurred are independent. So that's simply the probability of a tail. So that's the same thing as 1 over 2. The probability of a tail given that the other 2 tails has occurred is also independent. So that's also 1 over 2. So these are independent. And that way we now have this to be 1 minus 1 over 8. And that is simply equals to 7 over 8. Exactly what we got earlier. Pretty easy. That's the multiplication rule. All right, my friends. And so with this will be a much shorter video for the second part. So let's get into the whole concept of the Bayes rule now, and tie in the whole concept of the conditional probability that we just looked at. So Bayes theorem. So I said the Bayes theorem is a special application of the conditional probability. It is a way to formally incorporate the new information, and we'll see how. Because probability assessment of events of interest may be based on relative frequency or subjectivity. So it's a way to formally incorporate the new information. Where is my screen? Come back up here. Okay. So let's review conditional probability. Remember that the probability of B given A is equals to what? Put it this way. The probability of A occurring and then B occurring is equal to the probability of A times the probability of what? B given A. So this is what we saw from the conditional probability, which we established some videos above. Let me see. Yeah. So here we're building something. So probability of B given A. So looking at this here, we have the probability of A and then B is equal to the probability of A times the probability of B given A. So that's the multiplication rule, which we derived. Now, so we can say here that the probability of B given A is equals to the probability of A and B over the probability of A, right? In the same way, we can have that the probability of A given B is equals to the probability of A and then B divided by the probability of B. So we have these two equations in which to the right, the numerators are similar. So what we are having here is simply saying that, so if we equate this one and this together based on what is common, we have that the probability of B given A times the probability of A is equals to the probability of A given B times the probability of B. Why? Because this is equals to this, okay? So basically, this will be equals to this. All right, so with this, I can simply say that the probability of B given A is equals to the probability of A given B times the probability of B divided by the probability of A. This is the base rule. And the probability of A is known as the total probability, okay? And we can look at this through some examples. So that's basically it. And if there are any questions, we can also discuss this during our office hours, and I'm happy to go over some examples of the homework with you in order to bring more clarity on this concept. But in general, this is the base rule, and I'm giving you a task to investigate how to determine the total probability, which is the probability of A in the context of a given problem like this. So that's the base rule, and at this point, we are pretty much done with the second part. But let's see if I have an example that I can pull out to make it much. Let's look at one example, and then we'll call this video close. So let's say that, and I'm going to pick up an example from the textbook. I have an example I have here. Let me get this example. And we'll solve it together. So using the whole concept of the base rule. So here's the problem. I don't want to type it, so I'm copying it here. So we have here a regional bank has two branches, B1 and B2 in an urban area. 80% of the total customers of the bank use branch B1. Studies show that 40% of branch B1 customers are female and 70% of the branch B2 customers are female. Suppose a female customer is interviewed. What is the probability that she uses branch B2? Okay, so this is a problem given to us. The first thing we need to do is write out, convert this word problem into symbols. For example, what's the probability of B1? We said 80% of total customers of the bank use branch B1. So 80%, so that's equals to 0.80. So the probability of B1 is 0.80. Now, what are we trying to find? Let's say, what is the probability that she uses branch B2? So what's the probability of B2 given the female? That's what we want to find. The probability of B2 given a female. That's what we want to find. Now, we know that this probability of B2 given a female will be equal to the probability of a female given B2 times the probability of B2 divided by what? Divided by the probability of F of female. So how do we derive that? That's what I'm going to show you. Now, the probability of female, which is the total probability, is equal to the probability of B2 times the probability of female given B2 plus the probability of B1 times the probability of female given B1. That is the total probability. So we see, so the probability of B2 times the probability of female given B2 plus the probability of B1 times the probability of female given B1. That is the total probability. So now let's see if we have all these values. So we know what B1 is. Now, what's the probability of B2? So when you look at this, so a regional bank has two branches, B1 and B2, in an urban area. So B1 and B2 are complementary. So that means B2 will be 1 minus 0.8. So that's 0.2. Okay. Studies show that 40% of branch B1 customers are female. So what that means is that the probability of female given B1 is equals to 0.40. And a female, and 70% of the branch B2 customers are female. So that is the probability of female given B2 is equals to what? 0.7. And I think we have everything we need. So now we can proceed with our computation. So we have that probability of B2 given female, which is the probability that she uses branch B2, is equals to the probability, this is 0.7 times the probability of B2 is 0.8. No, B2 is 0.2 divided by the same thing, 0.7 times 0.2 plus the probability of, oh, I flipped it. I can always flip this. So the probability of female given B1 is 0.4 times the probability of B1 is 0.8. Just to be consistent with my numerator. All right, so I hope that all this is clear. If it's not clear, let me know. Now you can use your calculator to solve for this. You know, at the end of the day, you guys should be masters with your calculator. 0.7 times 0.2. I'm doing this because in your homework assignment, you have something related to a problem like this. So this is 0.14 divided by 0.14 plus, so what is 0.4 times 0.8? That is 0.32. So that is equals to 0.14 divided by 0.46. So we have 0.14 divided by 0.46, and that gives us about 0.3043. so to 4 decimal places. So we can stop there. So that is how to solve for this problem. So the probability that she uses branch B2 is simply this. So that's 30%. That's 30.43%. Awesome. And so with these, I have shown you an application of where we use the Bayes theorem. Okay. So this is an application of where we use it. And with these, we will come to the end of chapter 4. All right.